Everyone, welcome to another video, and in this one we are talking about Corrective RAG or Corrective Retrieval Augmented Generation system. In the previous video we talked about self-RAG, where we discussed how you can build a RAG with self-reflection that can catch hallucination in the model, or that can also understand whether the question provided to the system was relevant to the knowledge base or not. And in this one we are now actually building another flavor of RAG, and this is called Corrective RAG. It has also been picked from another research paper, which you can see the snapshot of the paper here on the screen. The title is Corrective Retrieval Augmented Generation, and what it does is also explained in the design here. So what happens is that it takes the question from the user, and it has multiple sets of node that does a lot of things, and with this it helps to answer the question. So the idea is, when a user gives the question, then the retriever nodes fetches the documents for the question. So what a retrieval augmented generation system is, that you have a set of documents, and for that, when a user asks a question, you have to provide an answer to it. So what happens is that you have a retriever node that fetches the relevant document for a question, and then you have a grader node here which grades each and every document, and if the documents are relevant to the question, then we go ahead and we directly answer the question, right? And if the document was irrelevant, or if any of the document was irrelevant from the retriever node, then we rewrite the query. So basically we enhance the query and then we perform a web search. So the idea is that we have a primary knowledge base which is embedded into the retrieval augmented generation system. That knowledge base is whatever documents we have provided to the RAG. But apart from that, we also have a secondary knowledge base or a fallback knowledge base, which is a web search. So if you will try to ask question which is not relevant to the document, or which is not relevant to the knowledge base present in the RAG system, then what the system will do is that it will gonna perform a web search after refining the query. So it will first refine the query, then it will perform the web search, and then it will get the answer. So the idea is to refine the knowledge base as well. So if the question is relevant to the document, then the knowledge base is refined internally. But if the question is not relevant to the knowledge base, then the knowledge base is refined externally by performing a web search. So we build a new knowledge base or an external knowledge base by performing the web search, and that knowledge base is used to answer the query of the user. So that is what Corrective RAG is. We're gonna explore this in detail going forward. I'll also walk you through the research paper on which we are building this, and at the end we will also be building this RAG from scratch, line by line, doing a code walkthrough as well, the way we used to do in our other videos as well. Okay, so let's talk about the introduction first. And the introduction is very cleanly laid out, saying given an input X and an accessible corpus containing a large amount of knowledge documents C, where C has a collection of documents, suppose n documents named D1, D2, D3 to Dn. Now the system is expected to generate the output. So if a user is asking a question as an input X, and we have a corpus of document, a list of documents D1, D2, D3 ... Dn, then the system is expected to generate the output on the basis of those documents, and that output can be Y, right? So the idea is, if suppose you have some internal documents, a lot of internal documents, and you want to train a language model on top of it, so that when you ask a question, the model can respond with some answer. Then the idea is you provide those documents to the model along with the question, and the model should be able, or your workflow should be able to return an answer. Now the entire framework is divided into two parts. First is a retriever, which is denoted as R, and the second is a generator, that is denoted as G. Now the retriever aims to retrieve the top K document. So you can think of this system is divided into two parts. First is the retriever and the second is a generator. Now the retriever comes first. When a user asks a question, the retriever goes ahead and fetches the top K documents from the corpus of the knowledge base, because we have a big corpus of knowledge base and it is not possible to provide the entire document as a context to the large language model because of a limited context window. So what the retriever does for a question, it only fetches the top K documents where the answer to that question, or the probability of having an answer to that question, is higher in those documents. So it filters out the document and basically fetches the top k relevant documents from the big knowledge base and name it as D, which is dr1, dr2, dr3 drk. So you can think of k top documents in the order which are relevant to the input X, obviously, from the corpus C. Now, based on the input and the retrieved result, the generator G is responsible for generating the output. So the work of retriever is done. It retrieved the top k documents. Now the control flow moves to the generator, where the generator takes the question of the user along with these top k documents, and it tries to generate an answer, or it tries to generate an output which is named as Y, and that Y will be returned to the user. Now this is the workflow which we are working on. And now the idea is, inside this workflow a lot of things are happening. Now the things can happen is that there can be a question which is not relevant to the document, and in that case the large language model can hallucinate, and we don't want that. We want our system to be fault tolerant. So what we are doing ahead is that we are coming up with an external knowledge base that is built on top of web search. So if you are asking a question that is irrelevant or out of topic, then this corrective RAG will able to identify that, and it will flip the knowledge base, and instead of going to the natural route of a classic RAG workflow, it will pivot and it will go to the web search route, build a new knowledge base, and it will gonna try to answer your question based on that knowledge base. So that is the idea. And let's move on to the definition of the CRAG. So CRAG, in short form, Corrective Retrieval Augmented Generation System, introduces corrective strategies in the traditional RAG-based system. So when the traditional RAG-based system can go wrong, it tries to correct it by providing some strategies. Now, a lightweight retrieval evaluator is constructed to estimate the relevant score of the retrieved documents to the input query. Now, the idea is we have a retriever and we have a generator. When a user asks a question, the retriever tries to get the documents, the top k documents from the knowledge base, and it tries to provide the relevant score to each retrieved documents. Now, if suppose you asked a question and the retriever pulled 7 documents from the knowledge base saying that these are the top 7 documents where I think the answer can be there. Now what happens is that, to avoid biasness, each and every, suppose all these 7 documents, each and every documents from those top 7 documents are treated independently, and a large language model is asked to score that particular document. So one document is given to the model along with the query, and the model is asked, hey, can you tell me or can you provide the relevance score for that query and the document? So the relevance score, when a large language model gives a high relevance score, means the answer for that query can be found in that relevant document. If the large language model gives a lower score, it means the answer to that query cannot be found in that relevant document. And with that, we provide relevance score to each retrieved document against the input query. Now, if the retrieved documents are irrelevant, then web search are restored to and regarded as a complementary knowledge source for corrections. Now that's what I mentioned. In the corrective RAG, what we are doing is that we are falling back on an external knowledge source which is accumulated through web search. And if the retrieved document are irrelevant, meaning if the large language model gave a very low score which is below the threshold to all those relevant documents, then we will think that these retrieved documents are irrelevant to the question, and there is no point of using those documents to answer, because in that case the model will hallucinate and will provide you with wrong answers. In order to correct that, what we will do is that if the system finds that the documents are irrelevant, then we will go ahead and perform a web search. When we perform a web search, we extract some relevant documents from the web search, from the big plethora of documents present on the web. We prepare our knowledge base using the web search for that document, and then we let the RAG do its work. So basically we build the knowledge base on top of using web search, and then we let the system, or we let the large language model answer the question on the basis of that knowledge base. So that's what a CRAG, or a Corrective Retrieval Augmented Generation System, is. Now let's quickly understand the paper as well. So this is the paper on top of which we are trying to build Corrective Retrieval Augmented Generation. Will not go into that complexity in which the things are defined in this paper, but we'll try to build something similar to a corrective retrieval augmented generation, or basically we are trying to build a RAG which will perform similar thing what corrective retrieval augmented generation or CRAG does. So this is the paper. The abstract is pretty readable and it should be understandable actually. I can read the most important stuff here. So we propose the corrective retrieval augmented generation to improve the robustness of generation. Specifically, a lightweight retrieval evaluator is designed to assess the overall quality of the retrieved documents for a query, returning a confidence degree based on what different knowledge retrieval actions can be triggered. Now this is what we have explained, that we have a retrieval and we have a generator. This paper is not talking about retrieval, where the retrieval is retrieving top documents for a query. That's what it says, designed to assess the overall quality of retrieved documents for a query. So it is basically assessing the quality of the retrieved documents for the user query. And how it is assessing? It is assessing by providing a score or a confidence degree to each and every documents, and then it is understanding whether those documents are relevant for the knowledge retrieval or not. Now, since retrieval from static and limited corpora can only return suboptimal documents, large-scale web searches are utilized as an extension for augmenting the retrieval results. So it is mentioning that static and limited corpora, meaning the documents or the knowledge base which you have provided to your RAG system, those are static and limited, meaning those are not open to change, while the documents present or extracted through web searches that change very frequently, and that's why they can have latest data or the things which are missed in your static corpora, right? Also, web searches can answer to a wide variety of queries. That's why what they are doing is that they are keeping web search as a fallback knowledge base. Now, besides a decomposed and recomposed algorithm is designed for retrieved documents to selectively focus on key information and filter out the irrelevant information in them. So what they are doing is that they are performing some knowledge refinement process through which they are filtering out the irrelevant documents, and they are only keeping the relevant documents with themselves. Okay. Now you can read a lot of things. It's a 16-page paper. I'll not go through each and every stuff obviously, but it is pretty understandable. Here is a image where it shows where a question is asked and it shows if the document is accurate, it can give a correct result, but if the document is inaccurate, then the model can end up hallucinating, or basically the generator can end up hallucinating. So I mentioned already we are dividing it into two parts. First is the retriever and the second is the generator. One more thing I would like to talk here is this interesting, very interesting diagram. Now this looks complex, but if I'll break it down, it will not look that complex. So the idea is, it is the CRAG process is divided into three steps: retrieval, knowledge correction, and generation. We already talked about retrieval and generation. What retrieval does, it picks or it retrieves the top documents for a question. So for example, the question was, who was the screenwriter for Death of a Batman? So it looks like it's a album, novel, or a movie or something for which the user is asking for a screenwriter. Now we have some knowledge base, and the retriever is retrieving top documents from that knowledge base for this question. Now the retriever retrieved two documents, D1 and D2, for this particular question from the knowledge base. Now we are performing knowledge correction, where the retriever evaluator is asking if the retrieved documents are correct to X or not, meaning if the retrieved documents are relevant to the question or not. Now three things can happen. First, the retrieved documents are correct or relevant to the question. Then it will go on to the knowledge refinement step, where what will happen is that these documents are further divided into strips. Now this paper mentions the strips to be a smaller part of the document containing one or two sentences. So you can think of these documents as big paragraphs or medium paragraphs, and these strips to be a very small thin strips of one or two sentences. So what we are doing, we are dividing these documents into thin strips, and then we are assessing the relevance of each and every strip. So now each and every strips is being assessed independently so that there is no biasness. So for every strips, we are assessing it for its relevance to the question which was asked. Now you can see there are two documents that was fetched from the question D1 and D2, which is being decomposed or divided into multiple strips. You can think of k strips here, strip 1, strip 2, dot dot dot, strip k. Now after performing this refinement filter, we are left with a couple of strips which is definitely relevant to the question, and that we are calling it as k-in, or I can think of it as an internal knowledge base. That's why k-in. In can be internal knowledge base. Okay. Second thing what can happen is the document can be ambiguous, meaning the large language model is not very sure that the document is very much relevant, or there can be presence of some document which is not relevant and some of the documents are relevant. That's why the model or the evaluator gave it an ambiguous score. In case of ambiguous score, we are providing a mix of both the things. We are performing knowledge refinement. We are also performing knowledge searching, right? So we are mixing both the knowledge bases. We perform knowledge refinement, we perform knowledge searching. If it is incorrect, meaning none of the documents was relevant, then we solely fall back to knowledge searching, where what we do for the query, we basically perform a web search. So this symbol is for the web search. So the query is death of a Batman screenwriter. The web search pulled some data from Wikipedia, and these chunks of data are now considered as the refined knowledge base or a fallback knowledge base termed as KEX or a external knowledge base, right? This is how things are. Now the third part is generation, which is very, very simple. What happens is that if it was correct, then we fall back to only the internal knowledge base, because the query can be answered through the retrieved documents which was pulled. So what we did is that we used the query X and the KIN, which is the internal knowledge base, to perform the generation of the answer. If it was ambiguous, then we need KIN and KX both, because for ambiguous here what happened, the control flow moved to the knowledge refinement as well as knowledge searching, and it prepared two knowledge base KIN and KX. So it is taking help from the internal knowledge base as well as the web search, and it is combining these two knowledge bases together to answer the query. If it is incorrect, then it is only falling back to the KX or the external knowledge base to answer the query. And these are the three ways in which the generation happens for these three cases, where whether it was correct, ambiguous, or incorrect, whatever the case is, this corrective RAG workflow will be able to generate correct answer for you. And that is why this interesting workflow is so beautifully explaining the entire workflow of CRAG. And I hope this is understandable. Apart from that, there are a lot of interesting things. This CRAG workflow has been benchmarked on multiple cases, multiple data sets, and the results are mentioned below. You can see here, this workflow was fine-tuned on Llama 7B model, and these are the scores. And CRAG is doing actually really well as compared to the traditional RAG and the self-RAG, which we discussed earlier in the video. I would also like to talk about the algorithm here, which is very, very similar to this image we discussed already. And this is the algorithm. What it does is that it requires a retrieval evaluator. It requires a query rewriter, which we will be using in our workflow to refine the query, and we are using a generator. Input is the question and the set of the retrieved documents, right? Y is the generator. Now, confidence is the confidence score provided by the model. It can be correct, incorrect, or ambiguous, which we discussed earlier in the diagram. Now, if the confidence is correct, meaning we only need an internal knowledge base. So we are performing the knowledge refinement, which we discussed above, and we are preparing the internal knowledge base. If the confidence is incorrect, meaning there is no relevant documents or the retrieved document are not relevant, we are fallbacking on the external knowledge base. And how we are preparing this external knowledge base? Using the web search. For web search, we are refining our query. which we will also do when we will build this CRAG from scratch moving forward. K is now we are preparing the external knowledge base with the help of the web search. So instead of K being internal knowledge, if the confidence is incorrect, K is the external knowledge. If the confidence is ambiguous, then we are fallbacking both on internal and external knowledge. Internal knowledge is built or is prepared by performing knowledge refinement of the retrieved documents, and external knowledge is prepared by performing web search on the refined query. At the end, we assign key to be the combination of internal knowledge and the external knowledge, and at the end, whatever the case is, we will have a knowledge base. It can be internal, it can be external, or it can be a mix of internal and external, but we will have a knowledge base, and that's why at the end we can successfully perform the prediction or successfully run the generator, which can predict or produce an output Y for a query X and a knowledge base K. That's what this paper is trying to prove, and I hope this is understandable. I will attach the link of this paper in the description of this video, so if you want, you can go through the entire through this entire paper. This is not a very old paper. It's just it was published last year on 7th October 2024, so it's very new and you should go through it. Now what we'll do is that we will move ahead and we'll implement this paper from scratch in Python. Time to build this corrective retrieval augmented generation workflow from scratch, and for that, this is the high level design of the nodes. So what we'll do is that we'll start from creating the model. For this, we'll be using a OpenAI GPT model. After that, we'll build the vector store. This we have done already in self-RAG. So we'll do the same thing. We'll build the vector store. We'll get the relevant documents. And now what we'll do is that we'll grade and filter the document. So what was explained in the paper, we will grade each and every piece of the document. We'll divide the document into strips and we'll grade each and every strip independently so that there is no biasness, and we'll see what document or what strips are relevant to the question and what strip are irrelevant. What we'll do is that if any strip is irrelevant, we're gonna filter them out and we'll only keep the relevant strips. After that, what we can do is that we can transform the query, or this is being divided into two steps. If there are relevant document after filtering, then we can directly go ahead and generate, because we don't need an external knowledge base. We can directly generate from the internal knowledge base and we can return the answer, right? If it is not the case, if the documents are not relevant, then what we will do is that we will transform the query, or in the paper it was mentioned query refinement. We'll refine the query and then we'll perform the web search, and we'll replace the internal knowledge base with the external knowledge base built on the web search. Now once the knowledge base is replaced with the external knowledge base, which we got from the web search, then we can generate the answer from the documents. So no way what happens, we will gonna go ahead and we will generate the answer from the documents no matter what. The only difference is we're gonna replace the knowledge base. If the knowledge base or if the documents are not relevant, we'll perform a web search and we'll use an external knowledge base. If the documents are relevant, then we'll keep those documents and we will keep those documents as the documents, and we'll again generate the answer from the documents. Once the answer is generated, we'll return it to the user and we will end the workflow. Now this is the high level idea, and this is the high level diagram of what we are building. Now let's move on to the code walkthrough. We'll actually see line by line how you can implement this, and after that we're gonna quickly run it and we'll see it in action. Now we are on the code walkthrough, and I'll just quickly open up the graph file where the entire code base of Corrective RAG exists. Let me collapse this, and this is the entire code base, or this is the entire script which implements the Corrective RAG workflow. It's around 230 lines, and I'm gonna explain it line by line what it does. So let's start with importing the libraries. So all these libraries are open source, and most of these libraries are LangChain libraries, so you can import that directly. After that, what we have is that we have our knowledge base URLs. So every RAG workflow has a knowledge base. on top of which it tries to answer the question. So for this workflow, we are building our knowledge base using some URLs of articles. Now these articles are from my newsletter. There are two articles which I am preferably using. First is what is word embedding in deep neural networks, and second explains what is backpropagation in deep neural networks. So remember, the articles are related to deep neural networks, word embeddings, and backpropagation. And if the question is related to these topics, then our workflow should be using the documents pulled from the knowledge base. If the question is irrelevant to these topics, then it should fall back on the web search, the way we explained in the CRAG paper. Now the first thing we do is that we define the shared state. Now shared state is the information which is passed from one node to another. If you're not clear about shared state, you should fall back to my previous videos, which is present in this AI Engineering 101 playlist. I have talked about shared state. I have talked about how you can build a workflow using LangChain and LangGraph. You should fall back to that, and you should, if you see my previous videos, you'll be able to understand, but this is not very difficult. So the shared state will have the information which needs to be shared. It has question, it has the response, which is provided by the generator, it has vector store, it has relevant documents, and it has the model, which is basically the large language model. We are using the chat OpenAI. For grading the document, we are also providing the structured output which we expect the large language model to follow. So while grading the documents, the model will follow this output, where it will provide you an object. Within that, it will have a binary score, and the value of the binary score will be either yes or no, saying whether the document was relevant to the question or not. Now the first node is getting the model, where we simply define the model and we put that in the shared state so that we can use it ahead. The model we are defining is chat OpenAI. The model is GPT-4o mini. The temperature is 0, and we are defining this model and storing it in the shared state. The shared state, you think of this as a dictionary, where against the model key we are storing the OpenAI model. Now then we are returning the shared state so that the execution can move forward. Second and one of the most important thing is building the vector store. Now we build the vector store on top of the knowledge base, which is extracted, or top of the documents which is extracted from the knowledge base. So what we do is that we pull the content from the URL. So web-based loader can be used. It's a LangChain library which you can use to pull the content from the URL. So it will gonna pull the content from my article URLs, and it will convert them into the list of documents. Now once we have these documents, we'll gonna build a vector store out of it using the OpenAI embeddings, because the large language model understand embeddings instead of text or natural language documents. That's why we'll convert our document into the embeddings, and we're gonna store that. Now we have a vector store with the embedded documents, which is built on top of our knowledge base. Now what we can do is that we can get the relevant documents. So what get relevant document does, given the question and the vector store, it will try to query the vector store for the question. So if I'm asking some question, it will try to pull relevant documents from the vector store. So you can think, I have the article, and I have given two articles. One is on backpropagation and another is on word embeddings. So if I ask the vector store to give some relevant documents on word embedding, it will gonna give me only those documents. It will not give me documents related to backpropagation and all. And this is very important because we have a limited context window, and that's why we should only provide relevant documents to the large language model so that they don't hallucinate. And that's what it does when we call an invoke method with the question. The vector store only picks the relevant documents which is relevant to the question, and it returns to us so that we can have the relevant documents. Now this is stored in the shared state as relevant documents key. Now I think we should first look at how relevant documents method work. So for that, I can again go on to another notebook where I can execute this cell independently. So before that, I'll go ahead and import the libraries which I mentioned earlier. I'll load the environment variables, and after that I'll quickly go ahead to this code. This is the code which builds the vector store. This is the same code which we saw earlier. In that place it was inside a method because that was a whole script, but here it is independently present because I can run this cell as a method, right? So when I run this, this will be able to build, this code will be able to build a vector store for me with all the documents present in the knowledge URLs. Now once the vector store is built, I can ask or I can query this store to get the relevant documents. So what I can do is that I can ask a question. My question is, what are vector embeddings? Now if I ask this, I'll get some documents, and these documents will be the relevant documents. So if I run this, I'll get the relevant documents. So this provided me relevant documents. I can showcase what the relevant document looks like. So it's an array and the size of the array is 4. So the vector store returned me 4 relevant document, and this is how the content of the first document looks like. And you can see a lot of spaces and all, because I think my article has a lot of spaces between the paragraphs. It has images as well. So word embeddings are a fundamental concept in deep learning for natural language processing, blah blah blah. So it is given a lot of details which it can find on word embeddings. And important thing to note is it has not provided me any other irrelevant information. It is only providing me the information which is relevant to me, right? Now we can go back to the agent graph which I was explaining earlier, and we were discussing the get relevant documents which we ran independently, and we see how you can get the relevant documents. After that, what we can do is that we can filter these documents. So in CRAG as well, we saw a knowledge refinement process where these documents are divided into knowledge strips, and those strips were independently queried or independently judged for relevance. And if any of those strips were irrelevant, it was filtered out. We'll perform a similar process here as well. We'll get the question, we'll get the model which we created earlier, we'll get the relevant document which we prepared earlier from the vector store, and we'll use a structured LLM grader with the structured output which I explained earlier, that the model will return a binary score of yes or no. We have a prompt which is important for grading a document. I can quickly show you that. So the prompt is very small. You are a grader assessing the relevance of a retrieved document to a user question. If the document contains keywords or semantic meaning related to the question, grade it as relevant. Give a binary score yes or no to indicate whether the document is relevant to the question or not. So if the document was relevant, it will provide with a score of yes, otherwise no. And the interesting thing here is we are doing this process independently for every document present in the list of the documents or present in the list of the relevant documents, because we don't want any bias. That's why we'll treat every document separately, and we'll basically assess every document separately. So that's why we are looping over the document one by one, and for every document we are invoking the retrieval grader with the question and the document, and we are asking that, hey, for this document, is it relevant to the question? If it is, give me a binary score of yes, otherwise a no. If the grader responded with a binary score of yes, then we are keeping it in the filter document, and we are printing grade document relevant. So we are grading the document to be relevant. Otherwise, we are printing grade document not relevant, mentioning the document is not relevant, and we are not adding it into the filter documents array. So initially this filter documents array is empty, and as the documents are filtered, and as the documents are considered relevant, we put that in the filter documents, otherwise we don't add it. After that, we update the relevant documents array with the filter documents. So initially we pulled some relevant documents from the vector store. Now we are performing an additional refinement process the way we saw in the CRAG paper, that in order to build the K-in, that is the internal knowledge base. So once the filter documents are prepared, we update our internal knowledge base, that is the relevant documents, with the filter documents, and we return the shared state. So now moving ahead, we'll use filter documents. Now the interesting thing here is what can happen if a question was out of context and if there was no relevant document for a question, then there will be no document with a binary score of yes, and in that case the filter documents list will be empty, and that can be used to decide whether we want to generate or not, because we have two processes, right? If we want to generate, we can directly generate from the relevant document. If there is no relevant document, we can perform a web search. This is the node which does that for us. If the length of the retrieval document or relevant document is greater than 0, meaning we had some relevant document, then we can generate answer from relevant documents and we can return generate. Otherwise, we can print no relevant document found, transform query and perform web search, and we can return with transform query. Now, if we say we decide to generate and we return generate, if there was some relevant documents, then this method will be called, which is generate answer from the documents. Here, what we'll do is that we'll take the model, we'll take the RAG prompt, which is a very standard prompt which we have discussed earlier in self RAG as well. It basically takes the context and the question and tries to answer. It takes the question, it takes the relevant documents, and it tries to provide the answer on top of this. So the model response will be the answer to the question I have asked, and the graph will end. If there was no relevant documents, then we need to perform a web search, and before performing a web search, we need to do the query refinement, which was there in the CRAG paper. So we perform query refinement, or here we are calling it transform query. So this method will be called, which will gonna transform query for us. For transforming the query, we'll take the original query and we'll take the model and we'll give the question rewriter prompt, and we'll also provide the initial question so that the model can rewrite or refine the question for us. Now the prompt is very simple. This is how it looks like. You are a question rewriter that converts an input question to a better version that is optimized for web search. Look at the input and try to reason about the underlying semantic intent meaning. Cool. So what the model will do, it will gonna rewrite the question for me and it will provide me a refined question that is helpful, or that is very helpful for a web search, right? That is optimized for a web search, right? So it will gonna provide me a question, or we call it a better question, which is optimized for the web search. We also print the transformed question here, and then we update the question with the better question. So now we have refined the question. That's why it is important to update the earlier question with the better question in the shared state. After that, we can perform the web search. So now we have updated and refined query for an optimized web search. So now we can use that query to perform the web search. This is also very simple. We'll use Tably search, which is an open, which provides an open API for performing web search through large language models. So what you can do is that you can perform the Tably search. You can bind this as a tool to the large language model as well, but here we are using it independently. So we are declaring a web search tool as Tably web search, and we are invoking it with our query, which is the question, which is picked from the shared state. Now this refined question is provided to the web search, and the result which we get from the web search is updated or replaced as a document. So remember, in the CRAG paper, we have this idea of updating the knowledge base with k out in case of we perform web search. That's what we are doing. Whatever document or whatever result we got from the web search, we are using that document now as a knowledge base. So we are updating the relevant document with the document obtained from the web search. And after this is done, we can again fall back to the same node, which is generate answer from the document. Now the only thing has changed is that we have updated the document with the web search result. So now the same question will be answered from the knowledge base, which was pulled from the web search, and again we'll get a similar, or we'll get a correct answer. And this is how you build a corrective RAG. Now these were all the nodes. This is how it is arranged in a graph. The first thing we do is that we define all the nodes. We have discussed this process when we were building self RAG as well. The second thing we do is that we build the graph. So to build the graph, we set the control flow. The control flow starts from the start node and always ends at the end node. Between that, we build the graph flow. So we start from the start node, we call the get model to build the model. Once we get the model, we build the vector store. Once we build the vector store, we get the relevant documents. We have explained all these nodes. When we get the relevant document, we grade and filter the document. So now here the interesting thing happens. Once we grade and filter the document, we execute a conditional edge, which decides whether we want to generate from the relevant document or from the web search. If we want to generate from the document, we can directly generate the answer from the document. If there were no relevant document, we can generate from transform query. This is what this method does. It returns either transform query or generate depending upon the condition, which we discussed here. It can return generate or it can return transform query depending upon the conditions. Now, if it the generate answer from the document will be called and the answer will be returned and the workflow will end. If the transform query node is called, what will happen is that it will gonna perform the query will be transformed or the query will be refined and then will perform a web search. After performing the web search, we update the knowledge base with the KX, that is the external knowledge base, and then we go back to the same node, that is generate answer from the documents. Now the document has updated, so we can again call this method which will try to query the RAG with the updated knowledge base. It will return the answer and the workflow will end. And this is the entire workflow. We'll gonna compile the workflow and then we'll try to run it with our questions ahead. Now let's try to run the workflow, the CRAG, the corrective RAG workflow, which we have discussed in so much detail. And let's start with a question which is very relevant to the topic or to the knowledge base which we have provided to the RAG. So remember, we have provided two articles, one on back propagation in deep neural network and second is on word embedding in deep neural network. So if the question is related to those, then it should be able to get some relevant document and it should be able to provide correct answer without performing any web search. So my first question is, what are word embeddings and how do they work? And then I can provide it to the graph as a shared state, and then I can get a shared state as a response once the graph execution completes, and then I can see what was the agent response in the shared state. Let's quickly run this. So it has start executing, and I guess most of the documents which it retrieve should be relevant because our question is very relevant to the topic. The grading document for relevance process has started. It has graded all the document to be relevant, and after that it is generating answer from the relevant document, and this is the answer. Word embeddings are a method in deep learning for natural language processing that represent word as dense real valued vector in a multi-dimensional space. This representation captures the semantic and syntactic relationship between words, allowing neural network to process and understand natural language more effectively. And this is really good. This is a correct answer, I guess, which is provided by the workflow. Now what we can go ahead and do is that we can provide an irrelevant question and we can see what happens. So ideally what should happen is that if a question is irrelevant, then most of the documents should get filtered in the knowledge refinement process and a web search should be triggered. The question we are asking is, explain binary heap. Now once this question is executed, I think most of the documents should be treated as irrelevant during the knowledge refinement process. Now let's see it in action. I'll run this again one more time with the new question which we have. So it should start the document grading process. Okay, it started, and you can see it has graded the documents to be not relevant, and I guess none of the document was relevant, so it transformed the query. Now it transformed the query, and the updated query is what is a binary heap and how does it work. And now it performed a web search. So it got the output and results from the web search, updated the external knowledge base, and finally answered our query. And this is how the answer looks like. A binary heap is a complete binary tree that satisfies the heap property where each parent node is either greater than or equal to or less than or equal to its child node. So it is mentioning both max heaps and min heap. This structure allows for efficient access to the maximum or minimum element. It is commonly used in implementing priority queues. And this is correct, but you see how the corrective RAG is correcting its responses by updating its knowledge base and falling back on an external knowledge base which was built using the web search after refining the query. So now this was it on Corrective RAG. We discussed the paper Corrective Retrieval Augmented Generation. We also built this workflow from scratch and we saw how you can execute this workflow. Now I hope this video was insightful and you should now be able to build a Corrective RAG workflow from scratch using LangChain in Python. And if you find this insightful, do like the video, share it with others, and do subscribe to this channel because we are building our AI Engineering 101 playlist. Currently, we already have 10 to 11 episodes in this playlist, which are very informative, and each episode deals with a different topic where we build some workflow totally from scratch, and we perform a code walkthrough as well where we go through that workflow, each and every part of the code line by line, and then we try to execute it. So if you found this insightful, then you should like this, you should subscribe to the channel so that you can be notified when I upload more videos under this playlist, and I'll meet you in the next video.